Hey guys, today we're going to talk about a cool device called the Mass Spectrometer, which is a great way to identify unknown compounds. It used to show up, I used to watch NCIS, and they'd always talk about their mass spectrometer and how they were analyzing various substances from different places. And it turns out a lot of the tricks for a mass spectrometer work really well with the stuff you've learned in this unit. And the basic trick I want you to pick up with this is how to equate the magnetic force to other forces if they're equal and opposite, or other forces if they're equivalent, to come up with new formulas. It's not too hard. It's kind of like F net cos equals F net circle, and that will be one of the examples. So a high-level overview of the device is, well, why don't we just start with the beginning? So first thing you need for a mass spectrometer is a really accurate thing that can shoot these. You got to ionize the particles and fire them off at a very specific velocity, but it's very hard to fire particles at a specific velocity, especially if you don't even know their mass or anything. So you can kind of ballpark it though. So if you fire particles in the ballpark of the right velocity down a tube, and this tube has perpendicular electric fields, notice these are the electric field heading up, and magnetic fields, which are into the screen. So if particles are flying down here and they're positive particles, because we stripped off a bunch of their electrons, the electric force and the magnetic force will be in opposite directions. If you do your right hand rule, it's probably flipped for you. Anyway, if you do your right hand rule, you'll notice that the magnetic force should be down and electric force would be up on a positive particle. It would actually work equally well for a negative particle as well. And the magnetic force depends on velocity. So if you can get your magnetic force exactly right, or your velocity exactly right, the magnetic force will exactly cancel the electric force and the particles will just zoom through. And if you've got a known magnetic field, you can just adjust your voltage between the two plates, and that you can use remember, electric field strength equals your voltage between the plates divided by the distance between them in meters. Anyway, so you can change the voltage between the plates, that changes the electric field, and from that you've got a velocity selector. You can change what velocity comes out. So if you want to figure out what velocity is going to come out, here's what you do. You've got your magnetic field equaling to your electric field when the velocity is just right, when the velocity is what you want it to be. Your magnetic force is the magnetic field strength in Teslas times the coulombs in charge. I've already crossed that out, so it's less obvious it's a Q. And your velocity in meters per second. And that will be equal and opposite to the opposing electric force, which is electric field strength, newtons per coulomb, times coulombs. Notice our coulombs cancel, and this actually becomes a very simple formula. Your magnetic field strength times your velocity equals your electric field strength, and you can solve for whatever you want, often velocity. So from that you can control what velocity particles exit here. If they're going too slow, the magnetic force will be less than the electric force, and if they're positive particles, they will be deflected up and smash into the top of this tube and not end up coming out the other side. If they're going too fast, the magnetic force will be bigger than the electric force, and it'll deflect them until they smash into the bottom side of the tube, and so they won't make it out. Only the ones in the Goldilocks zone with the exact right velocity will go through undeflected, and that's how you get a very accurate velocities of particles going into your mass spectrometer, which is our next part. So you put these particles, your tube would be coming out here. This would be the exit. They'd be firing out this way. And you just got a uniform magnetic field in an area, and like detectors along the sides. So your detectors are along the sides here. And what does a charged particle do if it's moving perpendicular to a magnetic field? It moves in a circular shape. So it'll immediately arc and smash into the wall. And while we calculate how we would figure out, like we will know what distance, what the radius of the circle it had to smash in the wall there, if we detect it right here. And given that, we can figure out something called the charge to mass ratio, which is a good way of identifying a particle. You will need to know what charge to mass ratio is. Let's go over it. So if you're solving your mass spectrometer, you know your velocity. And in this case, our magnetic force is our net force. That's our F net cos, and that's equal to our F net circle. So we're doing our F net cos equals F net circle trick. So BQV equals one of our circular motion formulas, our centripetal motion formulas, mv squared over r. We can cancel out one of our v's. And then there are two ways we can go, depending on what we want. The usual way you use a mass spectrometer is you solve for Q over M, and you treat that as one variable, and that is called your charge per mass ratio. You're taking your charge dividing by mass, and that's a quantity. And that is a big indicator. It lets you identify your compound, because different things have different charge to mass ratios after they've been ionized with a given voltage or whatever. Anyway, so this is usually what you use to identify it. Know what a charge to mass ratio is. You're just solving for Q over M. Treat it like one thing. That's it. And if you rearrange your formula, it would be MV over BR. You could also, if you're not solving for charge to mass ratio, say you're solving for something else, you can rearrange it in a different way. This is one of my favorite ways to arrange it if I'm not solving for charge to mass ratio, because no denominators, but however you want to do it. That's about it. This is the mass spectrometer, the velocity selecting part, where you've got the electric force equal and opposite to the magnetic force. In this unit, you might also have the magnetic force being equal and opposite to gravity. It's exactly the same idea, except instead of BQV equals EQ, it's BQV equals mg. So not a ton different. Remember your right-hand rules. Be good at equating formulas to come up with new ones. And that's pretty much it for this section. Love the mass spectrometer. It's good times. And thanks for watching. Please like and subscribe. Or not. You don't have to.